All right, so there was something that I forgot to mention last time about the discriminant, the b squared minus 4ac. So I did say that when the discriminant was negative, that means that it has no real solutions, or it's got two complex answers. And so the graph kind of looks like this, where it never crosses the x-axis. And I also said when the discriminant was equal to 0, you wind up with one real solution. So the graph will look something like that, to where it's barely touching the axis. And there's also the case where the discriminant is positive, or it's greater than 0. And when that happens, you get two places where it crosses. And I did say that they were two real solutions, but I need to be more clear there. There's actually two cases. So the first case is when the discriminant is equal to a perfect square. All right, and then the other case is, when it's not, when D is not a perfect square. Hopefully you remember what a perfect square is. Perfect squares are the numbers like 1, 4, 9, 16, 25, and so on. So the reason that these are special when it comes to the quadratic formula is, you know how you have to take the square root of this discriminant part? There's always that square root of b squared minus 4ac. Well, if this is a perfect square, let's say it's 25. I think we had that example earlier. If it's a perfect square, this comes out to be, there's the plus or minus, and then there's a whole number. Now, there's still going to be two real solutions either way, but when this happens, this means that the answers or the solutions are rational. Rational numbers just means that they are fractions, or they can be thought of as fractions. So those are your whole numbers. Those are 2/3, 3/5, negative 5/6. All fractions. That means the decimal version of it terminates. The decimal version will repeat, like 0.5 or 0.191919 forever and ever. Okay. It also means that the original quadratic, whatever equation you were dealing with, that it is factorable. All right, and that's a special property in and of itself. Being factorable is kind of nice. So let's say you were dealing with x squared minus x minus 2. This will break down into factors. It would be x minus 2 and x plus 1. And when I find the discriminant, b squared would be negative 1 minus 4 times a times c. If I find this discriminant, it's going to be a perfect square. Negative 1 squared is 1. You got two negatives, so it makes it a plus sign. And then 4 times 2 is 8. You get 9. And 9 is a perfect square, which meant that this original polynomial is factorable. All right, and that's pretty rare. You don't always get that. So it will cross the x-axis in two places, and where it crosses, they will be rational numbers. And the other case is, if it's not a perfect square, then the answers are irrational, and it is not factorable. Okay, so they're still real numbers. They're real, but they might be irrational. So that might be, let's say it was the square root of 12. Maybe 12 is your discriminant. Well, 12 is not a perfect square. So when you square root it, you get this long irrational number that goes on forever without repeating. All right, so that means your answers will not be fractions. They're going to be nasty, including square roots. All right. So it'll still cross somewhere, but it's going to cross at like an irrational number. So one thing you want to keep in the back of your mind is over here in this case. When d is equal to 0, 0 is a perfect square. So when you square root 0, you get 0. So it does fall into this category here, which means that the answer, not two answers, the answer is rational. It is a real rational number. And whatever polynomial you are dealing with is factorable. Actually, it's what they call a double factor, which we'll talk about sometime. All right, that's good.